This is LeetCode problem 139, word break. We have a string S and a list of strings. It's not really a dictionary. Word dict. And we want to know if we can build S out of words from word dict. So obviously, LeetCode can be built up with Leet, then code. Apple, pen, apple can be built with apple, then pen, then apple. Yeah, cats and dog does not work. If you use the word cats, then the word and, you're left with OG, which is not a word in word dict. And there's no other combination that'll give you the full string cats and dog. Cats and dog, whatever. We're gonna use DFS. I'll explain why at the end if I remember. It's DFS, not BFS. But it's really a recursive function that takes an argument I. I is my starting index, and I want to know if I can go from the starting index, really 0, to the end of the word, or end of the string S, using only words like leet and code. So if I can start at 0, I can use the word leet, I can use the word code, and I'll have my full string, and I'll be at the end, and that's good. If I start here, I use the word and, I can't use the word and or the word dog to reach the end, because the next two letters are OG, and neither of the words matches that pattern. So recursive functions need a base case. My base case is when I reach the end. If I reach the end, then I've built the whole word. Return true. And then I need to check every word, because you don't know which word you're going to use to build the next part of the string. So I'm going to check if I can put word to build onto my string, starting from I. I don't want to say it's starting from I going to J, where J is the index after you use all the letters in word. So it's just I plus len word. So I'm just going to check. Let's say I'm at index 4 in LeetCode. I need to put on 4 more letters to reach the end. Can I put on the first word? No, because they don't match the next 4 letters. Can I put on the next 4 letters? I can, because they do match these 4 letters. Code matches code. So to check if they match, I'll just compare the substring. If the word is equal to the substring S, I, J, then I can use that word. That's why I declare J. You don't have to declare J if you can keep track of that in your head, but I like to keep track of J because we'll check if we can use that. Because in the second example, yes, we can use the word and, but it's still not a good solution because there's no way to finish the string with an OG. And that is actually the recursive step. That is DFS J. If we want to see if we can build a word starting with and, we need to know if we can build the rest of the string after the and, which is OG, which is DFSJ. Hopefully that makes sense, because that's the key to a recursive problem. If you checked every word and you didn't find anything where you can return true, you gotta return false, because there's no way to build the whole string. And that should be just about my full solution to this problem. Great. Which will work for every example case. The problem is this is going to be a recursive solution that's going to call DFS many, many times for every word and every character in the string. So if I submit this, it should run out of time. And what we need to do to save a lot of time is prevent the recursive calls that we've already called. Prevent the repeat calls. We need to use memoization. Yeah. How to do that? Here's a little trick. Done. Just kidding. Obviously in Python, if you understand what you're doing, you can cache the function. Caching DFS means that if you call the same function with the same arguments, the return value is already stored in the cache, and it'll just return the return value without running the whole function again. But we're going to do that kind of, manually, just so we understand what's actually going on, because that's much better practice and much more useful for your explanation on your interview, in theory. Instead of cache, I'll call it memo. Cache would be a fine word too, but I'll call this memo. And memo will be basically the same as cache. It'll store either true or false if we've already called DFS. You can't fill it with trues or falses though, because if you write all trues or all falses, it'll think you've already called the function DFS when you haven't. So instead of true and false, I'm going to fill it up with nones. And none will mean that I haven't called the function. You could do this a lot of other ways, but this is how I'll do it. So my memo will be none, except none for n characters, for every character in the string, which means we don't know if we can build that string. But we have the base case, which I'll actually instead rewrite as a memo. Memo n should be true, because if we reach n, that's the end of the string, we can build the rest of the string, because there is no rest of the string. And nice, we don't need this anymore in our DFS. What we do need to do is check if we've called this function with I already. If memo I is not none. If you're a little lost, it'll make more sense once I fill in memo I. But if memo I is not none, that means our answer is in the memo, so we don't need to run the function again. Then return the answer. Then all you have to do is, before you return, store your answer in memo. If we're about to return true for I, then memo I must be true. And this will save us calling DFS again with the same I. Same here. If we're about to return false, then we'll store that false in memo so that we never call DFS with the same I. We already know it'll be false. And this should not run out of time. It should. Oh, I didn't actually write equals false. It should pass, no problem, much faster. Yeah, it did. Thanks for watching. Hope that helps with the recursive problems, actually memoization problems. But yeah, a memo is, if I've already run the function, it'll return the value I already got for the return. It'll save a lot of time in these recursive problems.